We're jumping right into a paper that suggests a pretty massive philosophical shift in how we approach visual pre-training. It's called Next-Embedding Prediction Makes Strong Vision Learners, or NEPA.
Exactly. And the core idea of NEPA is that the whole, autoregressive generative pre-training that made LLMs like GPT so successful, that can be ported directly to vision.
So next token prediction, but for images.
That's it. It uses a standard vision transformer, a ViT with causal masking, and its only job is to predict the next image patch embedding based on the ones it's already seen.
And what's really compelling is just how minimalist the setup is.
Oh, absolutely. It's incredibly simple. You don't need any pixel reconstruction, no discrete visual tokenizers, no complicated contrastive loss. The whole thing is just a single forward pass.
One forward pass, and the results.
They're strong. Pre-trained on ImageNet 1K, the ViT base model hits a very competitive 83.8% top one accuracy.
Okay.
And when you scale that up to ViT large, it gets to 85.3%. But the real proof is transferability. On a dense task like 80-20K semantic segmentation, it's getting 54.0% IOU.
Which really proves that this simple, scalable prediction in the embedding space is enough to learn really rich visual features.
It is. It's a big deal.
Okay, so let's really unpack that. This feels like it's not just another tweak on self-supervised methods like MAE or Dino. This is a different philosophy.
It's a completely different philosophy. You have to think about the two opposing camps.
Okay.
For years, we've been in the representation learning camp. You take a model like MoCo or MAE, and your entire goal is to optimize an encoder to map pixels to a static, fixed-dimensional vector, a feature.
Right, you're building the best possible feature abstractor, like a camera taking a perfect high-res photo that something else will use later.
Exactly. It's a two-stage process. You extract the features, then you use them. NEPA, inspired by LLMs, throws that out and goes all in on generative pre-training.
So it's not about creating a static embedding anymore.
Not at all. The model is trained to be a dynamic predictive system. It's modeling the data distribution itself. So inference isn't an extraction step. It's just a single predictive computation.
So you're forcing the vision model to behave exactly like a language model. You take an image, split it into patches, turn them into a sequence of embeddings.
And then you just train it to predict the next one in the sequence.
And that's what makes it different from something like JPAs, right? Which also predicts in the latent space.
Yes, JPA is still, a bit more representation-centric. It has momentum encoders, asymmetric branches. It's more complex. NEPA is just minimal. Yeah. Generative prediction is the only objective. A single embedding layer and an autoregressive predictor. That's it.
Okay, so let's get into the mechanical details. Predicting a continuous vector is tricky. How do you formulate the loss and, how do you stop the whole thing from collapsing? That's always the challenge.
It is. The mechanism itself is pretty straightforward. The model predicts the next embedding, and the loss is just negative cosine similarity.
So you're just trying to make the prediction vector and the target vector point in the exact same direction.
Precisely. You want to maximize that similarity. But as you said, that leads to the classic collapse problem. If the model gets too good, it just learns to make all vectors identical, the loss goes to a perfect -1, and it learns absolutely nothing.
So what's the fix?
The crucial defense, and this is borrowed directly from SimCM, is the stop gradient operation. You apply it only to the target embedding.
So you're cutting off the gradient flow on the target side.
Exactly. By preventing the gradient from flowing back to the encoder through the target, you're forcing the predictor to chase a constantly moving target. It can never just settle on one easy answer. The collapse is avoided.
That stop gradient seems like the one piece of necessary complexity here. So the autoregressive part is obviously central. What happens in the ablations when you start removing those constraints?
Oh, it breaks down completely. If you remove the autoregressive shifting if you ask the model to predict its own embedding from its input, it just becomes an identity mapping task.
It learns nothing.
Nothing transferable. The model just fails to converge during fine-tuning.
Yeah.
A total failure case.
Which makes sense. Prediction has to be about the future, not the present. What about the causal masking?
The second key piece. If you remove the causal mask, you're allowing bidirectional attention. You've basically just turned it into a masked autoencoder, but for embeddings. And performance drops significantly.
So that causal structure is absolutely essential for forcing the predictive objective.
It is. And what's really interesting is what happens with random masking. You'd think, like in MAE, that masking would help by making the task harder.
But it doesn't?
It actually hurts performance. We found adding 60% random masking lowered accuracy by several points. It tells you that the causal prediction task is already hard enough. Adding random noise just disrupts the sequence the model is trying to learn.
Okay, so let's talk architecture. The beauty here is that you're using a single ViT backbone for everything, right? No separate decoder.
That's right. A simple prenorm transformer does both the context encoding and the prediction. It really simplifies the whole pipeline.
But, and this is where we move from the simple objective to the complex reality. Training these deep transformers to be stable is a huge engineering challenge. What did you have to bolt on to actually make NEPA work?
Yeah, stability is never free. We had to integrate a whole suite of modern components from state-of-the-art models like Dino V3 and Visualama. They were all essential.
What was the most impactful one?
For the sequence structure, it was definitely rotary position embedding, or ROPE. It's just a much more natural way to encode relative positions for a sequential task.
And the performance gain was significant.
Massive. It gave us almost a 3-point boost in top 1 accuracy. It really proves that NEPA's success relies on understanding how those patches sit relative to each other in a continuous way.
Okay, so that handles the sequence. What about the depth? How do you keep it from exploding?
For depth, we first use layer scale. It's a simple trick that just stabilizes pre-training and helps it converge faster, especially early on. The only trade-off is that it can slow down fine-tuning a little, so we had to freeze the patch embedding layer during that stage to compensate.
A small price to pay for stable pre-training. And what about the gradients?
That's where QK norm, or query key normalization, was critical, especially when you pair it with a modern MLP like SWGLU. Without QK norm, the optimization just goes off the rails unless you use an impractically small learning rate.
And you used SWGLU mainly to stay aligned with other modern models.
Pretty much. We wanted to keep the architecture compatible with what's happening in both vision and language. The actual performance gain over a standard GLU was, marginal. But it's about future-proofing.
Let's get to the final performance numbers. The big story seems to be achieving parity with much more complex methods, but with a single forward pass.
That's the main takeaway. On Emergent 1K, our base model at 83.8% is right there with MAEB and DynoB. They're both around 83.6%. It's basically a wash.
And the large model?
Our VTTL hits 85.3%, which is just a hair shy of MAEL's 85.6%. So we're in the same ballpark.
But the efficiency difference is huge.
Oh, it's a different world. We use 1 forward pass per step. You compare that to MoCo V3, which needs 2, or iBot, which needs 4. You're getting top-tier performance with maximum efficiency.
And the features generalize. That's always the big test, especially for dense prediction tasks where these methods can sometimes fall down.
Right, but NEPA did really well. On 8020K semantic segmentation, the VITL model got 54.0% IOU. That's a strong result.
Which is critical. It shows the model is implicitly learning scene structure and local features, even without any explicit pixel-level objective.
Exactly. And what's interesting is that while we switched to bidirectional attention for fine-tuning on those tasks, which gives a slight boost, the model still performs really well using only the causal attention it was trained with.
Which proves the autoregressive embeddings are already capturing a lot of the global semantics on their own.
It does.
So how does this happen? How does a simple objective like predict the next embedding lead to this kind of complex object-level understanding? The qualitative analysis must have been fascinating.
It was. We looked at the attention maps, and they were consistently long-range and just strikingly object-centric.
What do you mean by that?
So if you gave it a query patch on, say, the head of an animal, the model wasn't just paying attention to the neck. It was allocating attention to its feet, its tail, maybe even a branch it was sitting on. It was looking at semantically related parts, no matter how far away they were.
So it's implicitly learning the concept of an object without any supervision. It's grouping things together.
Precisely. We called it distractor suppression. In a cluttered scene, it learns to focus its attention on a small, coherent set of patches that belong to the main object and ignore the rest.
And the embedding similarities back this up numerically.
That was the smoking gun. We saw that the predicted embedding for a patch had extremely high cosine similarity with other patches from the same object, even if those other parts were occluded or on the other side of the image.
So it's not just learning texture, it's learning to extrapolate object-level structure. The features themselves become semantically predictive.
Yes, that's the key insight.
This feels like a major step toward unifying vision and language models. I mean, if NEPA is just predicting the next embedding in latent space, that points directly to modality-agnostic models.
That's the most exciting long-term implication. You see LLMs moving toward tied embeddings, shared input and output matrices. NEPA's objective fits that perfectly. It suggests you could have one unifying objective across vision, text, audio, all using continuous embeddings as a common currency.
And because it's autoregressive, it's naturally generative.
Absolutely. You don't need a whole new model for generation. You could just couple NEPA with a good image decoder or a diffusion model, and that same predictor could be used for image synthesis, completion, editing. It bridges the gap between representation learning and generation.
Okay, but before we get too carried away, we have to talk about the limitations. Where does NEPA currently fail?
At the ImageNet 1K training scale, it definitely struggles with scenes that require a deeper physical understanding.
Like what?
Things like complex reflections on metal, really challenging shadows and lighting. It also gets confused by scenes with lots of small, overlapping objects. It tends to blur the semantic boundaries there.
So interpreting the physics of a scene is still a challenge.
It is. The hypothesis is that this is a data problem, not a model problem. We think scaling up to much richer, more diverse data sets should start to address these reasoning failures.
Which brings us to our final thought for you to think about. Given that NEPA's strong performance comes from capturing object-centric structure with just a simple causal objective, how much more general and robust could this one highly efficient objective become if we scale it beyond ImageNet to data that truly challenges its current limits on complex physical reasoning?